Okay, guys, so back to power consumption. Um, let's see, where were we? So I think the main thing was we had two components for power dissipation. One was dynamic power. That means circuits acting. So just to go very far back, the main thing you want to do with power, reducing your power consumption or keeping it reasonable, is to have as few circuits as possible operating at any given time. Because your dynamic power consumption, as soon as your circuits start switching, they start taking up dynamic power, and you want to keep that only in where needed. You don't want any unnecessary switching. So that gives you your dynamic power consumption. And then the rest of the circuits that are not on are still have leakage current. So they have the so-called static power consumption, which comes from leakage, et cetera, that we're talked to. But initially, dynamic power is what we were looking at. And it's usually, depending on the process node you're in. If you're in the tighter process nodes, like 65 nanometer, which this book uses, quite often, you're talking about maybe 30% of your power is in static power and the rest is dynamic power. And when you're looking at dynamic power, the only equation you have to worry about is CV squared F times alpha. So capacitance, your supply voltage squared, and your switching frequency. And this alpha is an activity factor. So basically, on the average, how often does this switching occur in this circuit? So this is really all you have to remember in terms of dynamic power consumption is CV squared F times the activity factor alpha. Here's an example. Maybe we can just kick off with this example. So once you guys take a crack at this thing, it talks about a billion transistor chip, and it's mostly memory circuits. So it has 950 million memory transistors and 50 million logic gate transistors. The memory transistors, their average width is 4 lambda. This is a 65 nanometer process. So you're looking at 0.025 microns per lambda. So like this would be, the average width is 12 times 0.025. 12 lambda times 5 microns per lambda. And same with the memory. So you can see the memory transistors, their widths are smaller because you got to pack them in tighter and they don't run as fast. And then each one is given an estimate of activity factor. I think we mentioned this last time, that when, sort of a rule of thumb for logic is about a 10% activity factor. And then the memory is operating much more infrequently because you're only grabbing, you're only addressing a few memory elements at a time. And this is giving an average capacitance. Okay, notice this is by the way, a lot of times when you see capacitance values, gate widths, etc., the assumption is you're running on a minimum length, you have a minimum length transistor. There's no reason usually in logic to make things longer than minimum length. So this is all in microns. This is assuming minimum length. So it's not an area number when you're talking about capacitance. It's giving it per micron of width. And then it's giving us a clock frequency of gigahertz. So once you guys take a shot at calculating that. And if you need to peek at the answer, it's just in the next slide. So if you have it. Have any of you guys watched this movie called shoot, I can't remember what it is. Let me think. Hold on. Let's see. The Val Kilmer movie. Science. Say mirrored science, but it's not there. Real Genius. Have you guys seen Real Genius? It's from the 80s, so it's a long time ago. Any Val Kilmer fans?
Nope.
Too old for you guys?
A bit old.
So there was this, so it's supposed to be kind of like based in Caltech and whatever. So there's this young kid, I don't know, he's like 16 or something, he's a genius, and he comes to school, and then like the first lecture, everybody's there, and then second lecture, this is back in the day, people would bring tape recorders with themselves to a lecture, so you tape the lecture. And then anyway, the sort of the running joke during the movie was, at the end he comes in, or middle of the movie he comes in, and basically it's a bunch of tape recorders, and the prof is like lecturing to the tape recorders. So I feel like that with the number of participants. I feel like we're like slowly dropping over the semester. So anyway, sorry. It's not going to be, sorry guys, I have to amuse myself as the old dude here and mention old movies. I'm not even going to say it's a good movie for you guys to go watch. It's probably not. I don't know. Okay, now that I successfully managed to disturb you guys and throw you off the track, anybody want to help me with the with this thing? And I'll jump in at the same time.
I would attempt to.
Okay.
I think I got the first, because I think you have to split it up, right? So you have to calculate the power for the logic part. So then I think add that, right, to the...
Okay, let's do it. So you want to do the power for the logic block first?
Yeah, so I haven't punched into my calculator yet, but I have... Okay. Hold up, let me... okay, well, accidentally deleted it. But it's going to be the voltage, which is 1 squared, right?
Yep.
Then times the capacitance, which you have to multiply that number that you're given. Wait, actually, do you take that full capacitance, so the 1.8, you add those two, right?
Yep, you'll add the two. So it's basically you end up with 1.8 femtofarads per micron.
Yeah. So then I think I converted the 65 nanometer to micrometer, right? Then I multiply that to get like the total capacitance, or is that?
Well, so this is what you have to do. It's giving you the average width of the gates in that block as 12 lambda. Okay, so it's these lambda-based design rules. And it's 65 nanometer process. Did I mention this lambda is 0.025 microns per lambda? I can't remember if I did.
I can't remember.
So to get so if you want to get the total width of all the transistors in the logic block. You say, okay, so the total width is, you got 50 million of these guys. And so that's 50 million transistors. You multiply it by an average width in lambdas, and then you multiply by 0.025 micron per lambda. Did I get all that right? So this is the total width, total transistor width for all logic, and which makes this the total capacitance for all logic. And remember, we got to be CV squared F times alpha. Okay, so we got V squared, we got C. F is a gigahertz, right? And that's what they told us. So that's giga is 1 times 10 to the 9th. So that's our F. What is that? 1 over seconds. And then it's giving us also some activity factor for the logic. And we multiply that here. Did that, you guys follow me there?
Yeah.
Okay. And then all of this ends up being 2.7 watt. But we're not done yet, because this was just for the logic. Remember, the chip has both logic and memory. So we got to do the same thing for the memory. Okay, so the power of the memory is, it's got the same supply voltage, so this is V squared, times, still, it's got, you know, we still have the 1.8 femtofarads per micron, times, we have a lot more memory circuits. We have 950 memory transistors, but each one is smaller. So we plug in 950 million transistors times, these were given as 4 lambda on average as a width, and lambda is still 0.025 micron per lambda. Okay, so this is total transistor width for all memory, and this is the total capacitance for memory. So times 1 times 10 to the 9th times, same frequency. It's still the same equation here. And then the activity factor is a lot less, it's 0.02. Again, because you know, if you think about memories, you're only going to go and grab words in the memory banks. And when you're grabbing stuff from memory banks, you're just addressing certain you know, out of those 950 million memory cells or bits that you've stored there, potentially you're only grabbing in each of those gigahertz cycles, you might be grabbing, I don't know, 64, 128, whatever, something like that, something reasonable. Okay, so although there's a lot more memory, the total power consumption, the memory is less just because of that activity factor. Sorry, it's more, but sorry, but it's still not as bad. So that is 3.4 watts. So the total power of your chip is just those two. So P logic plus P is 2.7 watt plus 3.4 watt is 6.12 watt. Okay, so that's your total power consumption for this chip. That was the example. So I feel like to me this is like the simplest. The CB squared F thing is like really, really simple, but it has, for some reason, it has a tendency to confuse you guys during tests and stuff. So just don't don't lose sight of this guy. All you're doing is trying to figure out what your total capacitance is, and then the activity factor say, and you're good to go. It's a pretty simple calculation. It's a pretty simple concept. Now, what's difficult is trying to manage all these things because you gotta unless you're really careful, this power can really blow up on you. I mean, imagine if the activity factor was like, I don't know, 0.2 instead of 0.02 for the memory. All of a sudden you're at 34 watts for the memory instead of 3.4, or you've oversized your memory transistors. Instead of 4 lambda width, you weren't as careful with the design, or you gave yourself too much margin speed wise maybe, and you made them 6 lambda or 8 lambda wide. So this is stuff to be careful about. Okay, so what do I want to say here? I guess I just said it. So basically what you want to do is to minimize how much of your circuits are on at any given time. That's the activity factor, and switching, capacitance, voltage supply, and frequency. Let's look at all this stuff. So I'm gonna jump through this activity factor estimation because I don't know. I think you guys aren't gonna like be in a situation where you're looking at a giant block of 50 million transistors and doing this activity factor estimation. I think you just have to use a rule of thumb, something. And you don't, sometimes your simulation tools will tell you what it is, sometimes not. You can just use 0.1 or somewhere between 0.1 and 0.01. But but one way to help reduce the activity factor as much as possible is this concept called clock gating. Okay, and think about the clock. I think I mentioned last time that the clock is, might be as much as 30% of the total power, of total switching power. Okay, and why is that? Well, so we got power is equal to activity factor times voltage squared CV squared F. Okay, so activity factor bad, right? For a clock, we are switching as much as possible. Your space, by definition, clock is switching every cycle, so the activity factor is 1. So right off the bat, bad news. Voltage squared, well, the clock's got the same voltage as anybody else, so that's okay. Now, capacitance. Imagine the clock in a 1 billion imagine a 1 billion transistor circuit. How many flip-flops you might have, how many latches you might have. You're going to have a lot of those. So the capacitance on the clock node is going to be huge capacitance. You're going to be driving, I don't know, like hundreds of thousands, whatever, of flip-flops, whatever, depends on your design. But it's a gigantic capacitance, so that's really bad. And then frequency, by definition, your clock is the highest frequency thing in your circuit. So everything about clock means high power consumption, okay? And so what you want to do is, even if you've turned off, let's say some, because of the way you set up your microprocessor circuits or your processor circuits, some circuits aren't really doing anything. They're still, unless you do something about it, they're still constantly getting clocked, right? I mean, we talked about a flip-flop, or let's just draw a latch, right? Was something like this. So even in the simplest case, when nothing's happening, you're still clocking the gates on your clock, even if these inputs aren't changing, right? So what you got to do is do this thing called clock gating, which means that you select where, circuits that aren't working. So this would be like a giant block where it's not supposed to be gating, not supposed to be working in this particular sequence, be working just now. Okay, so we've decided to, shut these guys down, and you actually gate, and this is showing a NAND gate with an enable. So you're gating the clock, you're turning off the clock, going to this whole block when it's not working. Okay, that's a huge, huge power saver, because again, the clock is a big part of your power consumption budget, and you got to do this. This is like activity number one, is clock gating. Although it can be very dangerous, and we've even very experienced designers, chip designers, logic designers tend to screw up this clock gating, because whenever you mess around with the clock, you can have a bunch of unintended consequences. For example, if you don't delay the enable logic or make it synchronous to your clock or to the inverse edge of your clock, you could easily, if this was a synchronous enable, you could, or disable, you could get a situation where you could get some extra clocks clocking your registers, and you could put your circuit into an unknown state before you go into shutdown or when you come after shutdown. Or it could be that you're going to get sort of runt pulses on your clock if the enable or disable is very close to your clock edge. So you're going to have a bunch of don't knows, or it can really, really screw up your circuit. But anyway, but you cannot live without clock gating elements. This is a must-have to get a reasonable power consumption. And all it's really doing is it's reducing the clock power consumption. But again, that's a big, big part of your power budget. Okay, so that's clock gating. So do it all the time, but be extremely careful, because you can really, really screw up. Okay, so the next thing, so that was the clock, basically reducing essentially the capacitance or activity factor, really. So you have a high activity factor thing, and on the average, you're reducing the activity factor when taking over the entire chip. Okay, so the next thing in the CV squared F. So I'll write this because I never get tired of writing this. CV squared F. So looking at the capacitance. So what do you do? Well, a lot of designers start with speed. We just got through talking about delay. We went through like three lectures on delay and speed, and it's funny how that also works on the job at work. Whenever you're designing something, you're trying to make it, the focus is on speed. You're trying to make it blazingly fast. You're trying to get it, give yourself as much margin as possible, because you're worried about timing, and so you make your gates as big as possible given the area you're given. But then after all that, when you try to calculate the power consumption, you realize that your power consumption budget blew up because you made your gates too big. You give yourself too much margin. And this kind of is a good example of the discipline you need when you're doing chip design or really any kind of engineering. Is you can't be fixated on just one spec. And so, you go down a rabbit hole of just speed. And believe me, this is like very common. And then you go look at power consumption, and you gotta go back to square one. In analog design is similar, but instead of speed, it ends up being gain bandwidth product or noise or something that you get fixated on, and then your power consumption blows up. For some reason, power is always like the last thing on everybody's mind when they're doing designs, because for that circuit or that pipeline stage or whatever it is that you're fixated on that day or that week, the power isn't going to seem like a whole lot. The problem is all of them, by the time you design all of them and you add all the power of the whole chip together, it blows up on you. Anyway, so sorry about that rant, but anyway, so oversizing the gates and just having too much logic, too many stages of logic, so you got to be careful with that. Another thing which we have not looked at yet is the capacitance of the interconnect. So which ends up, this is the next chapter we're looking at, but that capacitance of, imagine all the logic in this 1 billion transistor chip, how much wiring you have connecting all these things together. So it's a huge amount of wiring and a big part of capacitance. So, one of the really important things is something called floor planning. You got to look at your overall chip. If block A needs to be close, this is you never get a case like this, but if clock A is talking a lot to to block B, you don't want it to be on the other side of the chip. I want them to be sitting next to each other, so all your interconnect are as short as possible. Of course, it's never quite that easy, because D, E, and F are also talking to B, and they're but floor planning is huge in chip design. And then we talked about this already, about that inverters are the most efficient drivers in terms of speed, but also in terms of power consumption. So don't drive wires with NOR gates or 3-input NAND gates or something. If you need that functionality before you wire, do that functionality and then buffer it with an inverter or something like that. Okay, so that's capacitance. Okay, so voltage. Actually, before I talk about that, let me tell you guys, go back to this and transistor sizing. I wanted to say one more thing. We touched on it in the delay part of the discussion, but not a whole lot. But so let me just talk about it again. So let's say you had some block, some logic path, and we went through and did a whole bunch of work on what the optimal delay of this thing is. Let's say it's some delay D from input to output. Okay, so everything we did pretty much in that whole section was to optimize the speed to minimize the delay. But there is a trade-off between delay and energy, okay, energy consumed. So if I was just gonna, you just arbitrary units and arbitrary circuit, just to give you guys an idea, versus, energy or power, say, is you'll see an sort of an exponential case where, we did this D optimal, which is your fastest path or least delay. But in reality, that's also the highest, or not really the highest power consumption, but it's also a high power consumption case. The point is that you can throw as much power into, trying to increase the speed, but it's very hard to go in this direction. And it's exponentially more expensive in terms of power consumption. And we see this in digital design, you see it in analog design. Once you try to push the speed too far, given a particular design implementation, and your power just goes through the roof. Conversely, if you just back off the absolute minimum delay, your power goes significantly down. So you get a big, big improvement. So again, sort of going back to this gate size, and don't overdo the speed fixation, is that where you can, only go very fast or design your circuits fast when you have to. Let's say in a pipeline, something like that, and in your sort of your main data path. But when you don't, just even backing off a little bit off of that sort of bleeding edge of speed will give you huge improvements in power consumption. So just keep that in mind, because that's pretty common in a lot of things, but certainly in speed versus power in chip design, analog or digital. Okay, so let's see, where were we? So it's, again, CV squared F alpha. So the next one to look at is this voltage. And, the annoying thing about the voltage here in this equation is it's voltage squared. So like I mentioned last time, if you're in an older process with VDD is 1.8 volts, let's say around 2 volts, not quite, but it makes it easier to get V squared, is 4 volts squared. And if you're at a VDD 1 volt, VDD squared here is 1 volt squared. So just by your VDD changing by 50%, not just, it's not easy to do that. You have to go, this is a 0.18 micron process. This is a, 65 nanometer process. Your power consumption goes down by a factor of 4. So it's a huge reduction in power consumption. So that tells you, just to go off on a tangent about why people choose smaller, feature size processes. They are much more expensive from an NRE standpoint. So from a non-recurring expenses standpoint, the 65 nanometer process is a lot more expensive to design into than a 0.18 micron process. A 0.18 micron process, you might be paying between the mask set and the wafers for an engineering run, you're looking at $200,000, say $300,000. 65 nanometer process, you might be, looking at 2 or 3 times that amount. But look at all this stuff it gets you, right, in terms of power consumption. Right off the bat, your voltage supply drops, so your power consumption improves there. You have smaller circuits, means that you can pack them physically closer to each other. Just the same circuits are going to be closer to each other, so your wiring capacitance is going to be less. And then you can do things like parallel processing, which we won't talk about much in this class, but that's why you see things like 6-core, 8-core, whatever core circuits, that each one, they're backing off the speed of each one, but using multiple of them to, the power they save in backing off of the speed edge is more than sort of whatever the performance loss is, more than made up by having multiple cores. And it's sort of a winning strategy, is to doing stuff in parallel. So anyway, just sort of a tangent about why tighter processes are better. Okay, so now the voltage domain. So we want to, let's say you have a certain process. What do you do? Well, one of the things is remember that, or when we're talking about switching power, is IDS is proportional to VGS minus VT squared, or VGS, depending on which, whether you're in saturation or linear, but in general, you're dependent on VGS, the gate source voltage. And V gate source voltage always ends up being the VDD. Okay, so when you don't have high-speed circuits, you can also try driving them from a lower power supply domain. So, for example, if you are in a 1.8 volt process, you could, if you can live with the noise margin, you can run some of your slower blocks off of a 1.5 volt domain or something like that. They don't need to be as fast, so you can have multiple voltage supply domains in a chip, and you always do for other reasons as well. A lot of times your I/O circuits, your output circuits need to be, at 3.3 volt or 1.8 volt, or these, standards outside the chip. So, so you need to, and your core inside the chip is running at 1.2 volts or 1.8 volts, wherever you're at, 1 volt. So that's great. So you use different power voltage domains, but you have to be a little bit careful, because if different parts of the chip are running at different domains, you're going to have situations where a low supply domain needs to talk to a high supply domain, whether it's a control signal or whatever. And that situation you have to be careful about. Okay, so in that situation, you can have one of two cases. So you can have the high domain driving a low domain. Okay, so it would be, say, in this interface area, it would be something getting powered off of a high voltage, driving something voltage. Okay. In this case, you are okay, because if you look at the inputs, let's say the VDD high, for the sake of discussion, was 3.3 volts, and VDD low, for the sake of discussion, was 1.8 volts. Okay, so high value here would be 3.3 volts on the gate of this guy. Well, it's going to turn on the NMOS, right, for sure. And it's going to turn off the PMOS, because the gate of the PMOS is now even higher than its source, so it's really going to be off. So that's good. And the lowest voltage is 0, in which case the NMOS is off, and the PMOS has a gate source of 1.8 volts, and it's on. Okay, so everything works here. What the problem is, when you try to have a VDD low voltage trying to drive a VDD high voltage domain. So there, for the sake of discussion, let's say VDD low is 1.8 volts, so it reversed, and VDD high is 3.3 volts. So when you have that case, when you have a low, you're okay, low is 0, turns the NMOS off, PMOS is on. But look at a case where you have a high value. High value is 1.8 volts. So NMOS, whoops. So NMOS is on, which is what you want. But look at the PMOS. So PMOS, the V gate source is, what the heck is that? 1.5 volts. So the PMOS is also on. That's really bad news, right? That means you have this guy's on, this guy's on. You have an unknown voltage here, which is now, instead of one of them being on and driving that capacitive node, now you got sort of a voltage divider here. And you don't know what the value here, this voltage is. And you're just getting tons of current going from VDD high to ground. So this is a bad idea. Don't do that. So what you have to do is you have to make special level shifter circuits when you're going from VDD low to VDD high. You need to do, I'm not going to go into this, but it's a little bit trickier to design. But again, this is another one of those areas where people really get burned, because usually it's not just one signal that you're dealing with. Again, in a billion transistor circuit, you have lots of signals going back and forth between high voltage and low voltage domains. And if you get any of them wrong, your chip won't work. So you have to make sure you have these level shifter circuits. So this is, just to tell you guys, so this is basically has the PMOSFETs in a positive feedback loop. So when the VDD low happens, it'll basically it'll flip this sort of positive feedback loop PMOSFETs, and they'll drive the output all the way to VDD high. And you put those as a layer between your different voltage domain circuits. So that's very, very important. Another thing that's really cool, just a great concept, and it works great, although it takes a lot of work to build this thing, is you could look at the actual operating frequency, because how fast a particular logic block is going, and when it's going slow and when it's going fast. And you can actually put it in a feedback loop with a voltage regulator. So when it's going slow, you'll drop the supply voltage to the logic block. Let's say you can't completely put it to sleep, but let's say it's running slower, or it's doing something that's not so important. You can run it at a lower supply voltage, and when it needs to wake up and crank on some data, you increase the voltage supply and you go faster. So those are all nice tricks to use at a system level. Okay, so that was everything on dynamic power. So that's when things are switching. But like I mentioned, static, even the things that aren't switching, take up, because they leak, you take up static power. So I think I mentioned that in older processes, not a big deal. Not a big deal. But they really started getting high, sort of less than 65 nanometer process. That's when it started burning a lot of people. And might be as much as a third or higher.
Professor, is it because the number of transistors were very high in the newer processes?
Well, we'll see. But what happens is, in the newer processes, it's not just that they're very high, all of that is part of it, but even for the same number of devices, the power consumption goes up, because what happens is a big part of the leakage current is the off transistors leaking. Okay, and we assumed, if you look at gate source versus the drain current, this is the gate source, mind you. So you have, I mean, this is, I don't know, ID, whatever it is, log ID or something. So you have it turns on at VT. That was our assumption. Okay, it turns out that that's not really the case. If you guys remember, we have this sub-threshold current. So as you get below the threshold voltage, you still get a drain current going. And it turns out that, we'll see the equation, but it's a strong dependence on how far off below V sub T are. So it goes down by a factor of 10 every 100 millivolts below VT. Okay, so let's say you made this blazingly fast process, all that stuff, and you made your VDDs small. So you made your VDD 0.9 volts. Let's say this for the sake of discussion, because you want to reduce your dynamic power consumption. Okay, you made your VDD small. Now you've got a problem, because IDS is dependent on VDD, because VDD is VGS, right? So what do? You reduce your threshold, because your VDD minus VT. So when you drop your supply voltage, you'll also drop your threshold to get a reasonable amount of current when the device is on. But that also means if your threshold is at 100 millivolts, when your gate is at 0, you're pulling a lot of leakage current compared to when your threshold is at 500 millivolts. Because when your threshold voltage is at 500 millivolts, your 0 gate voltage is 5 of these 100 millivolt steps below the threshold value. That means you have 10 to the minus 5 less leakage current than if you were only 100 millivolt increment below your threshold value. Does that make sense? It's a little hard to grasp, but basically, yeah. So it turns out that the drain source leakage current is very dependent by how many millivolts you are below as you go below your threshold value, you get significant drops in that leakage current. And it's just one of those things, depends on, you get a factor of 10 drop every 100 millivolts. It doesn't matter what process you're in. I mean, let's see, we've got an equation here somewhere. So it's kind of an equation like this. And this S factor, now we're not gonna, probably don't have enough time. Well, I guess we could go through it, but this S factor basically stays the same regardless of the process you're in. These things are dependent on the body effect, whatever. So these are like process dependent, threshold voltages, etc. But this S factor tends to stay the same from process to process for a MOS transistor. So you have this situation where you want to be hundreds of millivolts. You want your off gate value to be hundreds of millivolts below your threshold value. And as many of those 100 millivolt increments you're below your threshold value, your leakage of current drops by a factor of 10 with each 100 millivolts you're below it. Does that make sense? So here, in all cases, V gate off is 0. Okay, and in this case, V gate off is 5 of these 100 millivolt steps below your VT. And in this case, it's only 3 of these 100 millivolt steps below VT, just because your VTs are lower in this case, right? And you basically end up getting a factor of 10 for every 100 millivolts higher in your leakage current. This is kind of a fundamental thing with the sub-threshold leakage of MOS transistors. And again, depending on the process, a few things will change, but not everything. This S factor doesn't change. I'm not sure that was a real good answer for you, but it's really kind of fundamental to how far below the threshold voltage you're in. And the more advanced processes, they were emphasizing they're dropping the supply voltage to reduce the dynamic power. And to do that, they had to reduce their thresholds. And all of a sudden, that really screwed up the leakage currents.
Right, it makes sense.
Yeah, it's kind of a sort of complicated scenario. And, I guess it's not inherently obvious because it took a lot of people by surprise. As I distinctly remember, especially a bit like Xilinx. I don't know if you guys you've used FPGA processes. I think it was, if I remember, I think it was the Vertex 5 node. All of a sudden, the power consumption, like the leakage power of that, the off power was about the same as the on power. And it just blew up that generation of Xilinx FPGAs just blew everybody's power consumption budgets completely. It was when we got bit by that too. So I remember it. But anyway, hopefully that somewhat answers your question. But anyway, long story short, in the advanced processes that you'll actually be working in, you really got to worry about this leakage power. It is a significant issue now. And the main reason is this subthreshold current. And, the problem is these numbers are small. This leakage current is pretty small compared to the on current. But as we saw, there are many more transistors that are off than are on. So in aggregate, that power tends to add up. It's still better than them all operating, but it's not 0. Okay, so let's, do we want to use this example? Yeah, what the heck. So let's do this problem. So I want to do this. Do I want to do this? Nah, this is too painful. Let's not do that because I think it's just a bunch of calculations. So let me just talk you guys through it. So this was, again, if you guys remember, we had, well, let me take a vote. Do you guys want to go through these number crunching, or do you want me to just go through it real quick?
Let's just go through it.
Let's go through it, yeah.
Okay. So again, just don't get wrapped around the axis, but just remember this. So we had 50 million logic gates. And I don't know, whatever it was, 950 million memory gates. And these had sort of a average width And these had, whoops. And these had an average width. Okay. Furthermore, it's saying that we have two types of VT devices on this process. That's another thing you see quite often to save power consumption. So for dynamic power consumption. So again, ID is proportional to VGS minus VT, either squared or VGS, depending on which mode you're in, saturation, linear, whatever. So when you have when you have a high-speed device, you'd like to make V sub t as low as possible, okay? Because you get as much current as possible. So you want your high-speed circuits to have this V sub t. If they're switching all the time, you want as much I sub d to charge and discharge those nodes. So you want threshold voltage to be low. Okay, but like I mentioned, that would make the leakage current very high for those particular devices. So what the foundry started offering is 2 or 3 different V sub t's per process, and you can mix and match. So you'd have an option of either having it using 300 millivolt threshold, so that would be a low, or a 500 millivolt threshold, that'd be a high. And you can have them sitting right next to each other on your design. So you'd sort of have your things that aren't switching particularly fast on this high VT, which gives you a much lower leakage current. And then the fast stuff is either on a normal or low VT, and it gives you a higher leakage current. So this tells you the difference between these leakage currents, tells you that the normal VT, quote unquote, where's my pen doing this? This normal VT is 100 millivolt lower than high VT. How do I see that? It's because there's a factor of 10. There's a factor of 10 higher leakage current for the normal VTs than it is for high VTs. Okay. And then it also tells us that, are you guys, anybody not following me? I feel like I think I've had too much coffee. I'm going a little too fast today, but everybody good? Is there anything where your guys are having problem observing?
I think I'm good. I don't know about everyone else. You guys good?
Who's not good? Who needs
Jafar, are you good?
I'm good. All the time I'm good.
Okay, great. I'll just, from now on, I'll tell you guys about an hour before class how many cups of coffee I've had, and you guys can have as many, and we'll all be in sync. All right, okay. So having said all that, and then furthermore, the problem tells us that 95% of the logic gates are using this high VT because, only 5% of our design is going fast. And then the last thing is that this gate leakage, which is another factor in our leakage. So there's like 3 leakage factors. Did I just jump ahead? I didn't talk about any of this stuff. No? Okay. So there's the subthreshold leakage. I think we talked about this, maybe 4 weeks ago. I don't remember. We're talking about, subthreshold currents, but just as a reminder, we have the subthreshold leakage. And this is the one that's a function of threshold voltage. and how far your zero is always a zero. Is how far your zero is below your threshold voltage. That's the important thing. So anyway, that's the subthreshold current. Then also starting in the tighter processes, you started having a gate leakage current. Which was also very disturbing when it happened. I'll bring this up in the phase lock loop class. But it's not, compared to the subthreshold leakage, it's usually not very much. It's not a huge amount. Okay. And then lastly, you have your junctions also tend to, so you have reverse bias diodes in your drains and your sources. So this is leaking to, so junction leakage. And that, the subthreshold leakage is leaking from drain to source of the transistor. The junction leakage is leaking from the drain or the source to the substrate. And the gate leakage is leaking from the gate to your channel or to your transistor. Okay, so anyway, the gate leakage is much less, and then the junction leakage is telling us it's negligible, so don't worry about that. Okay, so having said all that stuff, we use this, it said that 5% of, said 95% of the gates use high VT. So the normal VT, so this is calculating the width of the normal, it's only 5%. So that's where this 0.05 is coming up. So this is all those, this is the width, the total width of all normal VT. And so that's using this 0.05. And then the high VT devices, okay, include all the memory and then 95% of the rest of the logic. And that's this total width of all high VT. Okay, so you take all those widths, so you got this leakage current per width, per unit width. Again, this is subthreshold leakage. It's just a functional width because we're assuming the lengths are minimum. Okay, and it's, multiply 100 nanoamps per micron for the normal VT and 10 nanoamps for all the high VTs. Now, the thing that's a little confusing is you got this factor of 2. So after you do all this stuff, why do you have a factor of 2? Well, it turns out that, let's say you have an inverter and either, this is supposed to be off or that is supposed to be off, depending on what's, whether you got left with a high or a low here, whether it's whatever, 1.8, actually 1 volt or 0. So the way to think about it is there's only one, like on the average, only half the transistors are in a situation where their leakage mattered, because the other half are supposed to be on anyway, right? Because that's how, even if you're not switching, you left your CMOS gate in some state, some known state. One of them is on and the other one is leaking away. So that's why you do this rule of thumb where you, after the end of everything, you divide these leakages by a factor of 2. Okay, and then you basically get all those leakage currents, multiply them by your power supply. So VDD, and leakage. And you end up with power, the static power. And which wasn't too bad here in this particular example. If you remember what we were at, the dynamic was around, I think, 6 watts or something like that. Still pretty high. Like, so I'm like, when I started doing CMOS design, unless you were doing analog design, you wouldn't even think about static power consumption. You basically just assumed it was 0 because you had these older processes, 0.18, whatever older processes, that the leakage was really, really low. And even now, those older processes are still being used for a lot of biomedical circuits because people still have 0.35 micron processes and 0.5 micron processes. And the reason they're still there is because their leakage currents are really low. They don't run very fast, but you don't need your pacemaker. It's not going at a gigahertz. It's going much lower, but the leakage currents are a lot less. So it's, you still, if you look at what's available in the industry, especially for biomedical circuits, you'll see a lot of these older processes, and a big part of it is the leakage current. Okay. I think we talked about this. We killed that guy. Okay, so this stack effect, having transistors in a stack, so basically what it's saying is the leakage current is giving you a too high a number, because if it's assuming that all your transistors, let's say, are off, and you got them connected to VDD. But if you have like a NAND gate, like you have, in a NAND gate, you have, in a NAND gate, you have your pull-down transistors in series, as an example. And what happens if the gates are both off? This value, if both of these gates are off or 0, this guy sees a VDD because the PMOSFETs are putting a VDD there. But this intermediate node sees somewhere between, between VDD and ground. It just depends on the the off resistance values of these two transistors. So that has 2 effects. One of them is that this guy, the bottom guy, sees a lower drain source voltage. That tends to reduce the leakage current of the N1 guy. But even better, the gate source voltage of N2 isn't 0. It's, could be, minus 0.8, because this point, if this guy is, let's say is 0.5 volts, Vx, the gate source of this guy is 0 minus 0.5. So even if you have a low threshold, you're like 6 100 millivolt increments, or 8, or whatever your threshold is, below that. So having this stacked, the more number of stacks, you reduce this. And the leakage current, really, because you're going from the drain to source, if one of them has low leakage current, it's sort of cutting off the leakage path from supply to ground. So this guy N2 just ends up with a very low leakage current because of this gate source voltage being negative. Okay. Okay, so these are all the rules, or sort of summary of everything we talked about for controlling your leakage current when things are off. So, so I guess this is like, motherhood and apple pie, low leakage and sleep, and low delay in active mode. Thank you very much. So, that's pretty obvious. But anyway, to reduce the leakage, we want VTs to be higher, because, again, the subthreshold leakage is a function of how far your zero is from your threshold, how many hundreds of millivolts. So the solution, you use multiple VT values. Usually you have two at least, and only use the low VT values when things are, by critical, it means high speed. Okay, so the stack effect, we said, helps. So how do you use it? Well, even when a circuit is asleep, you left it asleep with known input values. Okay, let's say this NAND gate that we said is in sleep mode, along with, you know, millions of its buddies. And we could have left this in a whole bunch of different cases, right? You could have it be sleep with this thing being 0, and this thing being 1, this thing being 1, this thing being 0, so on and so forth, right? But basically, if you leave it in a mode when it's in sleep, with both of these guys being 0, you are making sure that this guy is enjoying the benefits of the stacking effect. So you're basically forcing, by known inputs during sleep, right before you put stuff in sleep, you put a known input in there that minimizes the leakage current. Okay. And then if you really want to get, again, and buy medical circuits or memories, etc., people actually mess with the well voltages, the substrate voltages, and they basically, in a way to, when things are off, they actually put them in wells, and they essentially reduce the body voltage compared to the supply, compared to ground. So you end up with a very big VGS, a very big effective threshold. Okay. And then I guess all I can say about the gate leakage is, you know, it's really, they do whatever they can to reduce it, and unless you're making analog circuits like sample and holds, things like that, usually don't have to worry about it very much. Just jumping across this stuff, and then junction leakage, it's saying essentially that it's not that important. Okay. So this is the sort of the last, let me see, do I have anything else I want to say? Nope. Okay. So just like, so we talked about clock gating being very important because the clock is such a power hog. So we wanted to make sure we gated that guy off. But the other thing you can do is also gate the actual power to blocks. So let's say you've got some block in sleep mode. Still there's leakage going through it because there's a VDD supply on that thing. But what if you know, is showing these PMOS transistors here. What if you completely disconnected the power from these gates that are supposed to be blocked off, right? So let's say you just turn off the power, this thing is now floating, this power gated block, and it just sort of drains off to ground or whatever, and so you don't even get leakage current as long as you size these correctly, okay, which is really nice. And this is something you can do when you want to go to extra power reduction, but you do have to worry about warning about a couple of things. So if your power gated block is just floating or going to get drained off, you better make sure whatever circuits you're driving, whatever circuit that block is driving, gets a known input. Okay, if it's just sort of floating, whatever it's driving that's not power gated is going to end up in some unknown state, or some state you're guaranteed not to want. Okay, so anyway, make sure you gate the outputs also of the power gated block. And then the second thing, there's also a penalty in that when you want this block to be on, you have this extra resistance for these PMOS transistors in the path of your supply. So when you're on, it's not as efficient as if you're directly connected to VDD. I'm sorry. You have these in series, so you just have to make sure that these don't affect your VDD too much. Then you have to worry about these things have a big drain source voltage across them for long periods of time. So they could have some reliability issues in the long term, but that's not a huge issue. You just have to account for it and size them appropriately. So anyway, I think both the clock gating, I would just say, is kind of like mandatory. So you have to do that and do it very carefully. This power gating is also a very useful approach, essentially to save the leakage current. And when you basically use it, and it's very useful when you have very, very low leakage current requirements, like biomedical circuits, things like that. Okay, guys, that's it for tonight. Any questions?
Nope.
Okay, so if not, then we're done with power, which is a pretty important issue, but I think we touched on everything. And on Tuesday, we're going to start talking about interconnections or wiring between, which is another very, very key topic. Okay, guys, have a great weekend.
Have a good weekend, Professor.
Take care.
You too,
Bye.
brother.
Good night, Professor.
Good night.
Thanks.